Hello, this is the first of the videos. This is for Chapter 1, Section 1 of the Knight textbook, and it begins with the story of Penelope the Penguin, which is this penguin right over here. I can pick up and drag the penguin and kind of make it move. And this is a whole chapter dealing with just the basics, the very foundations of the concept of motion. So imagine Penelope the Penguin is in some sort of snowy field and begins walking and travels some sort of path I've kind of shown with this dotted line here. And the point of this picture, and then Penelope ends up here, and there's another Penelope to show you where the penguin ends up. So the point of the picture is to define a couple of ideas, things that we're going to talk about throughout the course. And one is the idea of position, which I've put over here. And when we say position, we're going to talk about it as the location of an object in space. So space could be this, two-dimensional thing that we have on the screen right here. And Penelope the Penguin could be anywhere along this two-dimensional screen, but it's only at certain locations. Now, all of those positions that Penelope transverses, as shown by the dashed line, that shape is called a trajectory. This curving shape is the trajectory, and it's the path traveled by an object, in this case, our adorable penguin. So what I've shown in this picture are a bunch of different positions at equal time intervals. And what I mean by that is we took a picture, or imagine that somebody has a camera and takes a picture maybe every second, but definitely in equal time intervals, like maybe every 2 seconds, or maybe once every 3 seconds. And so initially, the penguin is here, and this is the same trajectory. One bit of time later, maybe Penelope is at this location here. And then at an equal time interval later, Penelope the penguin is over here, and so on and so forth. And what you're starting to see here is that a picture like this, which is a little like a stop-motion photography thing, it can start to tell you a little something about the motion. Like, for instance, this path from here to here isn't really quite as long. I kind of showed you over here that between these two time intervals, Penelope the penguin has only traveled about so far. But between these two time intervals, Penelope traveled much farther. Now, one of the ways that we can show this without having to draw a penguin, because we're going to study lots of complicated things that might be difficult to draw. Penguins are somewhat difficult to draw because they have beaks and webby feet and little flipper things. So we're going to use a particle model, and scientists use this too. Scientists talk about complex objects as if they're like particles. And particles are special because they have no dimensions to them. And we can use a dot to represent particles. So if I go back one slide, you can see that everywhere where previously there was a penguin drawing, I have replaced it with a blue dot. This whole picture is called a motion diagram. We're going to use these diagrams to give us a sense for what a motion looks like. It's a diagrammatical model. I suppose I could write that out really quick too. That when we represent something in the physical universe by using a picture, it's a diagrammatical model. Which, if you just break it down, is saying we're using a diagram to represent something. And again, we're seeing the idea here that in this time interval, the penguin only traveled about so far. And in this later time interval, the same amount of time, the penguin traveled further. So you could imagine what that's telling us about the motion of the penguin. We could start to get into concepts of fast and slow. That between this time interval, the penguin is traveling a little bit slower. Between this time interval, the penguin must have traveled faster. So here are the 4 basic models of motion that we're going to study over the course of the year. And it starts out with a straight line motion, which is the very first thing that we're going to be talking about in the course. So an example of straight line motion might be something like a bowling ball that's been thrown. Of course, some people throw with a little bit of spin on it, which makes the ball curve and stuff, but imagine a very simple bowling ball rolling in a straight line down the lane. And you might try to represent this motion with a motion diagram. And to do that, you would draw a dot wherever the ball is at equal time intervals. And if you did that, it would probably look something like this. Like just 1 second later, maybe, this ball would end up rolling over to here. And then you could draw a dot representing that it's at this new location. 1 second later, the ball might be over here, and you could draw a dot representing that new location. And the series of dots drawn, this motion diagram, tells you something about the motion of the bowling ball. Another thing that we're going to study is projectile motion. It's a more complicated motion. It's the motion of an object that's been thrown into the air. So imagine a person standing on the ground, throwing a ball up into the air. And if I drew a dot in equal time intervals, maybe every half a second, you would end up getting a trajectory. If you kind of connect the dots with this dashed line, you get a trajectory that's this arcing pattern. You might actually recognize what this arcing pattern looks like from previous math classes, but we'll talk more about that when the time comes. Circular motion, the motion of objects traveling in a circular path. So I kind of made a dashed line trajectory here that forms a circle, and I drew dots. Imagine an object that's traveling along a circle, maybe at a pretty constant pace. If I draw a dot every few seconds, as long as they're equal time intervals, I could see something about the trajectory of this object. And there's some special physics going on for objects traveling in circles. And the other type of motion that we will study is rotational motion. Now, rotational motion is only going to be studied by the AP portion of the course. And it's different in that I can't use a particle model to describe an object that's rotating, because particles have no dimension. You can never tell when they're spinning. If you think about it, you can tell if something is spinning because it has structure to it, and you see the structure changing as it spins. If you had a perfect dot, even like a steel ball, it's almost hard to tell if the steel ball is spinning or not, because every side of the steel ball looks the same. Take that all the way down to a particle. Imagine a steel ball that literally has no dimensions, no length, width, or height. How would you ever know if that object is rotating? So we can't draw dots to represent rotation. So the best that I could do here is I drew something kind of like a top. It looks a lot like a dreidel, actually. And if it's spinning around in this direction, this kind of looks like a counterclockwise direction if viewed from above. You can imagine it spinning and rotating. And that's what we mean by a rotational motion. And that's it. Those are the 4 basic models of motion. We're going to get into more detail in section 1.2.